So you may remember this from last summer when 500 flights were cancelled because of one data error. And Willie Walsh, who's head of IATA, estimated it cost £100 million. He isn't known for understatement, but anyway, it did cost a lot. He is known for understatement. NATS had a hot standby system, but that wasn't going to help because it was the data that was the problem, not the application. Although you could say it should have tested for that condition, but that's a bit harder than you might think. With this audience, I expect this slide describes the way you work. Not in many places where I work, but hopefully here. You release software only when all the tests pass. But then your application is vulnerable to whatever data is entered into it. And data changes all the time. You keep getting new data. So the data can hit your application by a number of routes. If anyone thinks of another one, do tell me. We'll go through these one at a time. User input. This stuff really ought to be obvious, but often isn't in the systems I find myself working on. So the data entered by users should be validated, usually using form controls and JavaScript, before it's sent by the form to the application. Mozilla, which does have some quite nice documentation in this area, says that you should check the data again when it hits the application, and I agree. In terms of form controls, I mean, date pickers are good. It means that the user gets visual confirmation of the date they're entering, and there's no confusion about date formats. If you're dealing with any kind of international organization, or even one in this country that has its terminal set, its client set to different date formats, that can cause chaos. Address lookups are easy and cheap in this country as well. But it's amazing how some really mainstream organizations don't use them. But again, you can be much more sure that the address will be correct because the user gets visual confirmation and it will be in a sensible format. Email addresses and telephone numbers are a bit more complicated. We'll come back to those. And another factor in this is user training, because there are responsibilities on both sides, but a responsibility of the users is to know that they just can't type anything anywhere. And some users get quite upset about that. Why won't it let me type this in here? Well, because it doesn't make sense. But that means explaining why that's important. Data from databases can be guaranteed to be clean in various ways, but not always, because the database can do a lot of the work for us, and we'll come back to this too. If the data arrives in a file, it's probably been interfered with by Excel. So that top box there was a text file. The only thing I've changed in that is the spacing so that you can see the columns. But that's what I typed in, opened it in Excel, closed it again, opened it in the text editor, and all those colored things have been changed. And it happens all the time. Phone numbers without zeros at the beginning. Who's come across that? The other thing is this byte order mark. A byte order mark, if you were using UTF-16, which hardly anybody uses, it tells you which order the 2 bytes in the character are. But Microsoft uses that to indicate to Excel that it's got a UTF-8 file. And of course, that would be really weird because only 98% of the world uses UTF-8 now. 98% of the web pages in the world are in UTF-8. So I and many other software developers and product companies have had to do extra work to deal with this stupid 3 bytes that Microsoft has stuck on the front of the file. Does anyone listen to Tim Harford's More or Less? There's a great program there, and the links there, so when you get the slides, you can look it up, about some really serious Excel errors done at national government level. And so that's enough on Excel. API calls, they're usually going to be an XML or JSON. And that does come with, those formats do come with metadata, but it's not like a database where the data in the database has to match the metadata. If you choose to create an XML file with data that doesn't make sense in terms of the metadata, nothing's going to stop you. So that has to be checked as well. And that comes down to us as developers. That's our job. Data from devices, Internet of Things. I was lucky to work on one of the early versions of early instances of a car insurance system where they put a box in the car with the customer's consent. They actually got some benefits from doing it. They might have lost some in terms of surveillance, but anyway. But the box in the car sent back data every few seconds about the location and acceleration in 3 directions, backwards and forwards, up and down and sideways. So you could tell things that were happening to the car and you could kind of grade the performance according to that. And occasionally we would get a latitude, longitude reading which was 0, 0. And that's a genuine, those are genuine numbers. It's that point down there, which is where the Greenwich meridian meets the equator. But if someone's going down the A3 past Guildford and you're getting all these points and then you get 0, 0 and then back to the A3 again, you know, that really messes up the speed and acceleration fees. Another more subtle thing that happens, so when I live in Kent, and if I'm going back in the evening on the train and it's raining, it's quite useful to check where I am sometimes if I haven't been paying attention to where the last stop was. So this is from an actual journey. So I was coming back along from the top left. There's a little red line there. I was on the railway line and going up there. And the signal from the, this was with Google Maps, which uses the same technology as the car insurance system. The signal from the box does tell you how accurate it is, because it will tell you how many satellites it could see. And that makes the difference between a 5-meter circle and a 100-meter circle, or none at all. In this case, it was big, and that circle was big enough to cover a road and the railway. So the next layer of software was saying, it's got a road and a railway, it's probably on the road. So the red line switched down there until the circle moved off the road and back to the railway, and it switched back again. So we were getting data like that with cars on the road, and that could be important because we were looking at people breaking the speed limit. They got bonus points for not breaking the speed limit. And if there's a place in Scotland where a motorway runs right beside the road, and we had one of those, and the guy complained because he'd had points docked, and actually it was because the low-level software had interfered with the numbers and given us something inaccurate. The other way you might get data into your system, if you have startup parameters or environment variables or some configuration files or something, hopefully those will be in your version control system with the release, and you wouldn't change them at runtime. But if there is a situation where you need to do that, or somebody's done it through bad practice, you've got to change those, check those values when they hit your application, and hopefully you can make sense of them, or at least detect if they're wrong. So that was a brief overview of source data. We're going to change gear for a minute and look at how defects work. And there's some counterintuitive things in here which you may or may not be familiar with. But typically, in a system with many components, and those components could be data or code, 5% of the components will account for 50% of the defects. That's been measured in systems from way back in the 60s, I think. It's in a book from that era. It's still true. But that does mean that many components are defect-free from the day they were written, which is great. But the third point is the one that's really counterintuitive, because you think if you tested this thing and you found lots of bugs and you fixed them, that's going to be really good. But actually, the thing you didn't know was how many bugs were in there in the first place. And what has been found is that the more defects you find in a component, the more defects are left in it after you fix them. And that applies to data encode. Now, this was some work that was done in '79, a long time ago. But they took this idea and plotted the number of tests along the bottom and the number of failures. And then for each component, so the black line is one that isn't very good, and you keep finding bugs in it the more you test it. So eventually you get to the point where you reject it. And the white one is the converse, where you do lots of tests, you don't find many bugs, you fix them, you feel more confident about it. I think the concept is worth bearing in mind, but actually quantifying it, and I think probably why this isn't used very much, quantifying it is impossible, because how do you measure the number of tests? How granular are they? How do you know where to put those areas? But I think understanding that general principle at least should give you the confidence, which you might feel intuitively is, I keep finding things wrong with this, I'm going to scrap it and start again. That's what you should do. So how can we test data? We mentioned some of these. And what we've got more to say about is databases and files. So I think the easiest way to test data in a file is to load it into a database and use the database facilities to help you do that. And how difficult that is depends on what database you've got available and the structure of the file. But if it needs to be structured data. I mean, everything I'm talking about really is structured data. I'm not the kind of social media and Google contents, not really. It's a completely different story, I think. So I use Postgres. It's a good database, it's free, and the copy command's great, and you can use CSV files. And CSV files, if they're used properly and they're very simple, work really well. I've seen people do all kinds of things with them, like putting double delimiters in, which is completely unnecessary. But anyway, so that's to get it into your database. So I'm going to illustrate this with a case study that I actually did. It's for a leisure organisation that did a deal with a supermarket chain. And the supermarket's customers got information and discounts on the leisure facilities. The leisure company got a list of contacts. And I got this file of, so I was helping out a team and they didn't really know what to do with it. And I got this file of 26,000 contacts to add to our database. So I had a quick look at it. Nice, simple structure, just a few fields. And the first thing I wanted to do was to get it into the database and then profile it. Now, you may have a data profiler. You can certainly buy some. You can also get one free off my website, because I don't sell software. I give it away. And this is the output from my profiler. The stuff on the first three columns on the left are from the definition of the table that I created to put this data into. And then the right 2/3 are things about the actual data that was in that file. So I created the table with very kind of lenient data types because I didn't know what would actually be in it, whether it makes sense. Allowed everything to be null. I didn't find many nulls except in the phone number. Tells you the distinct value count. And the top one's quite interesting. It's the club card number. And it's the same as the row count of the table. So that means it's a candidate key with this data set anyway. Card number, what you'd expect. Look at the email address, and if you can see, that's pretty small here. That one's clearly wrong. Everything else looks pretty plausible. We'll come back to one other thing that isn't. And then the two things at the right there, frequencies and patterns. Patterns are only applicable to strings, but frequencies for everything. So we'll look at frequencies. We look at the title. Oh, I should say this is fake data. What I did was take the profile of the real data and create fake data that was very similar. I was a bit wrong on the kind of high-level titles. There's rather a lot of generals and brigadiers in there. But the Mr., Mrs., Miss, and Ms., those, so the three female ones add up to about the same number as the male ones. That doesn't prove anything, but at least it's a plausible number if you're dealing with this kind of data. Those frequencies can be more useful in some other kinds of data. Patterns. So the characters in the string are classified according to those groups. So 9 represents any decimal digit. So these are phone numbers. The little s is a space. The plus sign down there is any mathematical symbol, although with a phone number, it's quite likely to be a plus because that's a valid thing to put in a phone number. So we learned just from loading that data and running the profile that the club card number is unique. Always starts with 7. It's always 16 characters long. So that's great. Consent 1 and consent 2 are always yes. Otherwise, they wouldn't have got into the data set, I presume. So they're just not interesting. And this was a fixed thing. You know, they ran it once after a year of offering the service, and then we had that one file. So we weren't going to get any more. The email address has some errors. We'll come back to blah, 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 blah. Phone numbers are inconsistently formatted, but that's okay. Oh, and they've got this convention MX where people don't want to give their gender away by their title. And they put it as XMX, so that was just a simple change. Validating email addresses. They're defined by several RFCs. You probably know our requests for comments. They're not quite standards, and although they didn't make it into being standards, that's as far as it got, and they pretty much define the standard. Maximum length seems to be 320 characters. I think you'd have to be very masochistic to have a 320 character email address if you really like typing. Some characters are not permitted in some places. Some email clients don't accept email addresses that fit the RFCs, and other email clients do. But again, you'd have to try quite hard to get one that doesn't work. And there are dozens of validations available on the internet. And the one we used didn't reject any valid email addresses and did reject quite a few invalid ones. So it's useful, but not infallible. The highlighted bit in yellow is the key bit. Regular expression. If you're not really familiar with regular expressions, that link there is really good because it explains how they work and it tests them for you. Really good. So that one does work, and there are errors in those which I'll highlight for you. And you can see we've got something indicating an invalid character. We've got right arrows, all kinds of things, double dots, double at signs, I think, somewhere as well. So these are genuinely erroneous email addresses. And what the organisation I was with was very good in, where they've got an invalid email address or an invalid phone number, they try the one that looked valid and see if they could get it confirmed. Because you can guess what some of those should be, but we shouldn't be guessing about data. We should try and confirm it, really. Telephone numbers are really much more complicated than you might think. and people do write their telephone numbers in different ways, and Ofcom actually says that you should be able to. That's fine. But if you write that one, it could be the country code for Kazakhstan is 77, and that number is some corporate network in Kazakhstan, but it's probably a UK mobile. It would be good to check, but that's one I might guess, I think. Government Design Guide refers to Google's lib phone number, Java library of about 4,000 files. But even that's not foolproof, and Google says so. You know, it doesn't validate everything properly. Where I was working, they didn't want Google stuff and 4,000 Java files, so we wrote something simpler, and the source code is available, but it's nowhere near as comprehensive as that. But we use reference data from Ofcom for the UK numbers and from something called International Telecommunications Union, which gives you all the country codes. So we put all that in, you just copy those numbers and validate it. And what we found in that data was 2% missing, that's fine, they don't have to give us their phone number. 3% had errors, and all kinds of types of errors. So again, we hope that the email address is right and we can check these, because again, you can't safely guess. Right, so that's that kind of error. Another thing that comes along a lot is duplication. If you've got a reasonable sized database of data about people, you've almost certainly got some duplicates in it. I've never seen one that didn't have. When you're inputting a new file, that may duplicate data that's already in the database. And it may have duplicates in it as well. So finding duplicates is quite important. I won't go to this because I'm talking too much. But this is how Microsoft suggests doing it. Microsoft splashes AI all over all its marketing material. It's got the most stupid thing for finding duplicates that doesn't work. There is something that does work, which is great. And Microsoft's got this function in its Databricks product, because it just recently bought that, but not in its mainstream thing. Levenstein edit distance was invented in 1965. And it's really simple. It tells you how many single character edits you have to do to change one string into another. And it's a standard function in Postgres. So changing banana to Panama, you just have to change the P and the M, and that gives you 2. Changing pomegranate to Uzbekistan is obviously a few more changes. So what we can do is look for records where the Levenstein edit distance is small. Obviously, if it's 0, then they're exactly the same. But this method, which I haven't got time to go into in detail here, but it's on my website, and it's got all the code as well, how to do it. But this one over here, for example, can't see it because I'm standing in the way. Prasad and RR Assad, same first name, exactly the same first line of the address, exactly the same postcode. That's almost certainly a duplicate, and the RR Assad is almost certainly an entry error. So that is one I might change just anyway, but mostly, again, the best thing to do would be to actually check which thing's right. But that's far more effective way of finding duplicates. Right, the next thing is missing data. So data exists somewhere, but it's not where you want it to be. This happens especially if you're synchronizing with other systems. I've done quite a few data migrations where, we're taking data out of a live system and putting it into what's going to be the new system. But of course, that's changing, so you've got synchronization issues with that. And again, how not to do it. The product that it was going to was being installed by and customized by a $48 billion international consultancy. And I asked the project manager how he was going to make sure that our 80 million transaction table was actually the same when it got into their system. And he said, oh, well, we'll eyeball a few records, of course. It's like taking a handful of straw out of a haystack and expecting to find the needle in it. So, anyway, again, there are better ways of doing it. It can be a challenge if you've got two different data sets in different systems. And especially if they're changing, if you can get a kind of synchronization point, then at least, count the records. Did you get the same number as you started with? But you can be much better than that. You can count by some partition of them, like the year they were created or the month they were created, whatever. If they're financial records, you can check the total amounts. They should come out the same. And those kind of queries aren't really expensive. You're not comparing each record with each record, but actually those aggregate values. And we can also use hash values like you do if you're downloading files. So we can actually see if, at least try to see if the data is going to match. How am I doing for time now? 26. Perfect. So once we've done all our checking, then things are going to keep on changing. And we want to monitor our data as it's on its way into the system. And we have a tool for this thing as well. This was a real one. This one only had about 100 tests each day, but I have run this with up to 1,000 tests a day. In systems, well, we'll come back to how you fit all those tests in. But what it does, in this case, it was organized by subject areas and how many errors we found. And you can see on this particular day, we found an error in the transactions and in the merchants subject areas. And when we look at transactions, drill into that, this is measuring the actual value for the number of transactions and the change from the previous day or the previous run, mostly daily runs, these kind of things. And that change was really pretty big compared. Oh, it's we measure the size of the change, not the sign. So it could be plus or minus, but it's a big change. And the average transaction value, likewise, although if the value is 249 and the change is 897, then it's probably a decrease today. So then we get a graph of it. And what the monitor does several types of graph, but this seemed to be the most useful one because it records the date and the value and the change. And it assumes that your data falls into more or less a normal distribution. It's not guaranteed at all, but very often the case. It's very often close to that. So the green area is where today's change is within 2 standard deviations of the mean, which for those of you who are mathematically inclined would be 95%. If it's a real normal distribution. The yellow area is where it's between 2 and 3 standard deviations from the mean, which is about 4%. And the pink is anything above that. And it would account for about 0.3%. So you would expect, if it is a true normal distribution, that you get about 1 a year in the red. Here we've got 2. So what happened? So this was a financial payment processing system. And I would come in every morning and check those charts and find this. And on this day, Friday the 13th of April, 2018, it looked like that. I thought, we must have loaded the transactions twice. But anyway, we checked into it, and Of course, that's not measuring Friday the 13th in any way. That doesn't make any difference. It was actually recording what happened on the 12th of April, 2018. Anybody know what happened then? It was the Grand National. For anyone who's as interested in horse racing as I am and doesn't know what that is, it's a big horse race. And what had happened was people had started betting using payment cards. And that accounts for a huge spike in the number of transactions and the fact that the average transaction was smaller. Millions of tiny bets. So when we checked it out, it wasn't a problem. But you can see that being able to detect that kind of difference just by an automated process that runs overnight and then somebody, looking at a couple of screens, that's quite powerful if something's gone wrong. So it is automated. We would run it every night. The tests are written in SQL. They're very simple. You just have to write a SQL query to return a date and a reference to the thing you're measuring, a factor ID, we called it, which has got some metadata describing what it is, and the value. And then it calculates everything else from that. Again, it's on my website, and you're welcome to use it. If you do and you want to contact me, that's great. But if you all call at once, it'll take a while. So since this is most useful in a live system, we have to be careful about what impact we're having. So often there's a quiet time at night, but often there are batch processes running at night time. We have to look at how much of this testing we can do and coexist nicely with other things that are there. So standard risk analysis, what's the probability of a so far unidentified defect, and what would be the impact? And as we've seen, impacts of this kind of things can be very high. The match flight plan error was £100 million or something, and post office Fujitsu thing, well, that's just horrific. But that was presumably application error or possibly human error, but it was affecting the data, and if you'd been monitoring the data, you might have had a better chance of finding it. So our default setting is to run all the tests every night. If that's taking up too much time, I've only found one case where we were starting to bump into time that was needed for something else. So what we did was to run different tests on different days so that over the week we cover them all. And also, if we've got some data that we're really confident is static, then we can test it even less frequently. So you can apply the risk analysis. I wanted to sum up. Yeah, doing right. To sum up, I wanted to classify the sort of things that I thought we could do to improve the situation. And I came up with these 4 categories, but it's fuzzy because many things live in both categories. But anyway, let's go through them. So, looking at behavior, I mentioned users, working with the users, and of course, if we're all being good Agile developers, we will be working with our users all the time. So hopefully they will have automatically a better understanding of what the data is doing and why it might be important. But that's something to really bear in mind and work with them on. But they have to have the features they need so they don't improvise. Because if someone's trying to do his job and his boss wants it done by this afternoon, and our system won't do it for him, then he will improvise and things get bad. That happens especially with duplicates, of course. If they can't find the person that's on the phone in the system already, then they'll create another record. And it's not their fault. We have to work with them. On policy, Excel is useful. I mean, I do use it. Someone was talking this morning about pivot tables, and yeah, I do that. But not to prepare data. And yet that is Microsoft's recommended way of getting data into Dynamics, apart from users entering individual records. But when you get things like you know, our thing from the leisure company and the supermarket. What Microsoft said is put it in Excel, load it in. Well, it's a disaster. And it was a disaster, actually. I don't see any reason for not using UTF-8 everywhere now. But again, Microsoft still thinks we should use Windows 12.52. When you find a data error, just like application testing, add it to the test suite. Because, as Hunt and Thomas say, the first time a human being discovers an error, a defect, that should be the last time a human being discovers it. It should be. It should be in the test system. Avoid large package solutions. This is kind of a personal bruising from the last 5 years of trying to help people with Dynamics and Salesforce. They just seem to be defect factories, those things. And they use common data models, which is another really bad thing because your data will not match a common data model. No matter what you're doing, it won't match a common data model. So you'll put data into fields that have a description that clashes with it or has the wrong data type or something. So, and it's not hard to build your own data model. It's much harder to try and cram it into a common one. So don't do that. Windows, I've tried to avoid Windows ever since 1984 when the Mac came out, and it's been, you know, at first it was a losing battle, but I did work on Macs for a long time, but I'm so disillusioned with what Apple's done recently, I've switched to Linux now for my client. But importantly, I would always use Linux for a server system. I wouldn't run SQL Server on Windows Server. It's horrible. So design issues. So we're trying to trap data errors at the gate. And to be fair, the NAT system did trap a lot. A lot of people said afterwards they'd had flight plans rejected. So it wasn't that they weren't trying to do it, it's just that they missed that particular case of two waypoints having the same name. You know, you think of all the things you can test and you're going to miss some. XML and JSON as input is fine, but don't store those strings in the database. Split them up into their separate fields, because then you can process those. Well, you can get the database to make sure that each field is the right data type. And you can do all kinds of other things with those individual fields so that it's much harder to do if you're trying to pick them out of XML or JSON strings. Don't repurpose, I mentioned that before. Don't deprecate things. You know, if there's something in your system that's not right, but people are used to it, and you come up with a better one, make the change. Take the pain, do it now, refactor it, and change it. But when you've got two versions of something there, and one's deprecated, and they're both in use, that's horrid. And it creates inconsistency. Someone else mentioned this morning as well. Don't create flexibility that the users don't need. Sometimes, this would be a really cool feature. Nobody cares. Don't put it in there, because it's just another thing that can go wrong. And store anonymized data separately rather than plonking the word anonymized in all over it. There's a page on my website about that, but about how you can do it a different way, which is much better. But we haven't got time to go into that. Tools. This is almost all about databases. You know, I wrote it all down and thought, it's all about databases. Well, I went through the phase with a couple of organizations when they fell in love with data lakes. For structured data, a relational database is the best thing we've got. And if someone knows something better, tell me, but it ain't a data lake. And use database constraints. They're not expensive. You know, when I first started with databases, a constraint on a column was, something that would really impact performance. It's hard to measure it now. And that will stop wrong data getting into the database, even if it gets through the application validation. Reconciling, I mentioned. Profiling, I mentioned. Automatic data monitoring, I mentioned. So, that's it. And I Left some time for questions? Oh, not much. A little bit.
There you go. 5 minutes for questions.
Okay. Yes. Well, it's tricky because, you know, with where we got the 0, 0 ones, obviously we remove that and calculate between the points outside. But for that one, it was really tricky. And as I said, it happened with the car insurance system where the two roads were close together and the speed limit on one was 30 miles an hour and the speed limit on the other was 70. And we really need to know which one the car's on. So we had access to the people who were doing the low-level software, taking the data from the boxes and then presenting it to us. And it took a big fight to convince them that they shouldn't fix things for us. You know, we really needed that thing about how accurate it was, like how many satellites it could see. And if it's wrong, don't try and fix it. Just tell us, and then we can deal with that in the application. I think without that information, the application really hasn't got a chance of fixing it. So it's important to kind of surface that a level up. Yeah. Oh, thank you. Yeah. Well, the aggregate functions in the database work, but it's very easy if your structure is quite complicated to miss something that go into the aggregation or to duplicate it. And what I would try to do, and what I've encouraged teams to do, is if we're doing some complicated query and we get an answer and it looks plausible, then find some other way of trying to calculate parts of it or all of it a completely different way and see if it matches. Because far too often, well, it certainly happens with Excel spreadsheets, where people work on it and tweak all kinds of things until they get an answer which is what they expect, what is plausible. But people do that with databases as well. And it's part of the discipline of the developers that even for trivial queries, you know, you should check to see that the results you get are as true, that you have the highest confidence in them that you can. And it's amazing how, especially if you're working on, well, most databases, sadly, you don't often find one where you can't simplify the structure or match it up better to what the business model actually is. But even with a clean model, when you get a complex business requirement, your query can get quite long. And it's really, really easy to make wrong assumptions and stuff. So the best way I know is to, well, pair programming is great because the other person might, why are you doing that? And also just finding a different way of doing it, see if you get the same results. Yeah.
So the situation where you're importing data and the deduplicating of that, do you have any tricks or anything for dealing with situations where it might be like an actual update when you adjust changes and stuff? How do you cope with that?
Yeah, well, I've worked on quite a few data warehouses, and you know they get refreshed every day with what comes in. But sometimes you want to keep history, and this could happen for other kinds of things where you're synchronizing two systems or doing a migration. So sometimes the source system will tell you the created date and the updated date of the thing, and you can then deal with those either by if it's an update, changing it in the target system, or building a history, which is quite, it's called slowly changing dimensions, which it's just a history table. And it's in a lot of source systems as well. You have created on, updated on, and then you see the values that have changed. And that's usually quite useful in a data warehouse. With financial systems, you should never get updated records, although you often do. When a value goes in wrong, like a new person typed in, expected when they typed in 10,000, that would be 10,000 pennies, and therefore would be recorded as £100, but in that system it wasn't. So it comes in as £10,000. So the correct thing, which they did do, was to put in a new record which has a correction or a journal entry which says, referring to this transaction, but here's a new transaction which is minus 9,900 pennies. Whatever it was. Anyway, so it gets it back to what it should be. But that means anyone auditing that can say, okay, this was wrong, but we fixed it, rather than losing that important information. Yeah.
We're out of time, but thanks very much.
Okay, thank you. Thank you very much.